All right. This is CHEM103, and this will be guidance, instructions on how to perform lab number 7, molar mass of a volatile liquid. First, I want to show you where the material can be found. Everybody knows about Blackboard, so you have to go into Blackboard, and I'm going to share the Blackboard screen. Here we go. So you'll go to start here, of course, in CHEM103, and go down to your exercises. Here. And for now, all that's in there is the hard copy of the method, which you'll have to print, and the data that you will use. And I will share those screens and show you what they look like in just a moment. So now this is what the actual method will look like. Molar mass of a volatile liquid, sometimes called the Dumas method. The problem with calling it the Dumas method is Jean-Baptiste Dumas created lots of different methods. And it depends on what discipline you're in as to which one is the Dumas method. But he did develop this method, and we're going to use it to determine the molar mass of a liquid that is volatile under reasonable conditions, say in boiling water. Okay, so that, and then the data will look like this. Okay, so you have everything you need here to perform the experiment. I just have to show you how the data was obtained. So here you have the barometric pressure on that day, and this is in inches of mercury. There's your universal gas constant. There's the unknown code number. That is, the volatile liquid that is being used has an unknown code of 3, and in the method there's a table that has several volatile liquids, and when you determine the molar mass of your liquid, you match it with that table, and then part of the process of reporting is going to be to identify the unknown based on its molar mass. Okay, this won't mean a lot to you now, but these values are here. There's the mass of the flask. There's the mass of the flask with the unknown in it. There's your temperature, and there's the volume in milliliters. Okay, so let's stop that share, and let's talk about molar mass again and how we're going to determine it. All right. So in this semester, we've had at least one other way of doing molar mass, and then if you're with me again next semester, we'll have other methods of determining molar mass. But in this case, we're looking for molar mass, which I often abbreviate as molecular weight, just showing you how old I am. And in order to determine molar mass, you need two values. You need the mass of the compound in grams, right? And then you need to know how many moles are represented by that mass. Okay. So you need to know the number of moles. Okay, if you know those two values, you can calculate the molar mass of the compound. Right? Mass is easy. We get that by difference. We weigh the container without the substance in it, and we weigh the container with the substance in it. And the mass of the substance or the compound is the difference. Right? The real trick is finding out how many moles that represents. Okay? So we've got some help there from some giants of chemistry. Not just Dumas. Dumas proposed the method, but he was basing it upon earlier work by Avogadro. Remember what Avogadro said? If you have two containers that are exactly the same volume and that are at exactly the same temperature, and are exactly the same pressure, then you know that each one has exactly the same number of moles of gas. So what that's the beginning of the story. Others took that and ran with it. One of them, by the name of Cannizzaro, used it to propose a new system for determining the molar mass or molecular weight of various elements and compounds. And it's a good thing he did, because, well, I won't go into those details because we do that in lecture. But what came out of all of this was Avogadro's law. And I won't go into that either because we do that in lecture. But I will say, eventually, we came up with the ideal gas equation. I say we, science came up with it. Okay? Pressure times volume is equal to the number of moles times the temperature times the universal gas constant. Okay? And for our purposes, the pressure has to be in atmospheres. The volume has to be in liters. This is moles. And this is in Kelvin. Right? So that's why the units of measure for R are liter atmospheres per mole K. And the number that goes in front of it is that. Okay? So if you have a gas in a container and you know the pressure applied to the gas, you know the volume of the container, you know the temperature at which all of these conditions exist, then you can calculate how many moles are in that container. Right? So that's how we get the moles. We just need to know these values for our volatile liquid while it's in the gaseous state. And if we know those values, we can calculate the number of moles. All right? So, in the handout, the author of the method, the exercise, combines this equation with the universal gas equation, so that you only have to do one calculation. You're welcome to use it, but for discussion and illustration purposes, I'd rather do it the long way. Right? We know this. We get that from difference in weight or mass, and we use the gas equation to get this value. Then I put them together, and we calculate the molar mass. So I'm going to do an example problem for you in a few minutes. But before I do that, what I would like to do is describe the experiment. Right? So if you were doing this hands-on, you would need several things. You would need a container to hold your the gas. Right? So we're going to, in this experiment, we're going to use 125 milliliter Erlenmeyer flask. You see, Erlenmeyer flask is like that. Right? Shaped like that. And it's nominally 125 milliliters. Right? But that's only up to somewhere in here. It's marked. Many times they have graduated markings on them. But your gas is going to be confined in all of that space. Right? So you can't use that value. You have to actually determine what the volume of that flask is. Actually. And no two flasks are exactly alike. Right? The manufacturing processes are not that good. So what you will do to determine the volume, the simplest way is just to fill it up with water right to the brim, right to the top where you're going to place your cap. You want the position of the water there to be at the same level as the cap that you're going to put on it. And I'll describe the cap in a moment. So once you fill it up, then you pour it into your graduated cylinder. Right? And there's your volume. Just measure the volume of the water. And then, of course, you want your cylinder to be dry. So you've got to dry it out, or you have to do the experiment first and then do the volume. Right. Okay, so that gives you, let me put these up here. Let's put them over here. P, P, N, T. Remember in lecture I described, if you know these four values, you have completely described a gas. An ideal gas, really. There are other values that come into play if you're talking about a non-ideal gas, but we're talking about an ideal gas here. So now we've determined this one, right there. So where do you get the pressure? Well, the pressure that's applied to the gas is atmospheric pressure, what's bearing down on the gas. And the reason we say that is the method calls for you to put into this flask the liquid, about 5 milliliters. And that volume is approximate. It doesn't matter how much. Just 5 milliliters is a good place to start. So we put 5 milliliters of the unknown in here, right? It sits on the bottom. And then you submerge it in boiling water. Okay? So there's your water bath. And you try to submerge it as far as possible. And you put a clamp around it that goes over to a ring stand. Right? So you can lower it and raise it up without burning your hands. So you put it in that, and there's a cap on it. Before you put it in there, you put your liquid in there, and then you put a cap on it. Right? What's the cap composed of? Let's take this and blow it up. Right? So here's the top of your flask. So what you're going to do first is you're going to put aluminum foil. And then tie it off with a copper wire. So this is aluminum foil. There's your copper wire. And then you're going to take a bigger piece of aluminum foil and cover the whole thing. And just put a rubber band around that. Now, why would we bother to put 2 pieces of aluminum foil around that? Well, notice what's happening. You're submerging this flask in water. So think about potential errors. In order to get the weight of the gas in the container, you need to know the dry weight of your Erlenmeyer flask. But we're going to get it wet, right? So it needs to be dry when you weigh it, both before and after. So if you only had one piece of foil in there and a little bit of water got up underneath the foil, you're, as they say in impolite company, you're screwed, right? Because you've added weight that's not your gas. So what we do is we put an extra big piece of foil around there and cinch it down. And that one is not part of the weight, right? You weigh your flask dry with the copper wire and the small aluminum foil together as your tare weight. That is the weight of the flask and the apparatus, the aluminum foil and the copper wire. You weigh those first. That's the empty weight. Then after the experiment, when you weigh it again, you remove the big foil. And the big foil has protected the inner foil from accumulating condensation or splatter water up underneath, right? So then all you have to do is just dry the outside of the flask. And then you weigh it again with the gas inside. Okay, so that's why you have the extra aluminum foil cap on. But that's not going to be part of your weight. That's always removed before you weigh it each time. Okay, now we've put the 5 milliliters of liquid in here. What do we mean by a volatile liquid? Well, in this case, the liquid has to be reasonably volatile, that is, have a high vapor pressure at the temperature of boiling water, right? So if the liquid has a boiling point of less than 100 degrees centigrade, considerably less, we probably wouldn't want to go much higher than 85 or 88 degrees. Anything above that would be wouldn't be volatile enough. So you'll notice in that table of the various liquids we choose from, I think the highest one is maybe 86 degrees boiling point. So we've put the liquid in there, we put the small cap on it and the large cap, aluminum foil cap on it. Now we submerge it and we poke a pinhole in the top through both pieces of aluminum. So that's how the vaporizing liquid escapes. Now, why did we put 5 milliliters? Well, that's enough. As it vaporizes, it expels all of the atmosphere that's in there, oxygen, nitrogen, whatever else. So the only thing that's left in there is the vaporized liquid, the gas that forms from the liquid. And the hole is small enough so that you don't get any backflow from the atmosphere. As long as you keep it in the water bath, then there's enough pressure, and we reach an equilibrium pressure, at which point you want to take the flask out. Well, how do you know? Well, the method says leave it in there for so many minutes. Sometimes you can see convection currents coming out the top. It's very difficult to see those, but sometimes it's possible. But eventually, all this liquid vaporizes and nothing is left in there except the gas. Okay. At that point, you want the temperature of the water. The temperature of the water is the same as the temperature of the gas inside the flask. So there's your temperature, right? We got the volume, we got the temperature. Now we need the pressure. What's the pressure? The pressure is atmospheric. It's barometric pressure. And that is read in the lab, and it's in the data file that I showed you earlier. It's atmospheric pressure in inches of mercury. But the pressure has to be in what? Atmospheres. So how do you convert inches of mercury to atmospheres? You need a conversion factor. Right? So if your pressure is in inches of mercury, you need a factor you need a factor that will convert inches of mercury to atmospheres, right? So what's the equivalence? Well, I'll give it to you. 1 atmosphere is 29.92 inches of mercury. So you divide that number into the barometric pressure and you get your atmospheric pressure. And I guarantee it's going to be less than 1, right? Right, because here in the Beckley area, we're over 2,500 feet, half a mile high. So you're never going to get 1 atmosphere pressure. It's going to be a fraction, 0.9 something probably. So once you've got that, there you go. You got that, you got that, you got that. Solve for that with the universal gas equation, right? And if you solve for the universal gas equation, you get N equals RT over P. No, wrong. RT on the bottom. P on the top. There you go. Okay, so that will give you the number of moles. And then you fit that into your equation. But we don't have the mass yet, right? You have to weigh this beforehand with the small cap and the copper wire together. Okay. Then you do the experiment with the big cap on the outside. And then you take your flask and let it cool. So what's going to happen when your flask cools? Where's the gas going? It's going to convert to a liquid, right? So once it reaches room temperature again, and the temperature is stable, so when you put it on your balance, your weight doesn't go up and down like that. Whatever gas was contained inside the flask now is going to condense back into a liquid. But it's not going to be 5 milliliters. Right? That's why we didn't care in the beginning about 5 milliliters. We only care how much is in there now once it's condensed, because that represents the gas that was in there before. See? We don't create or destroy mass, right? That's true. One of the first principles we learned in chemistry. You can't create or destroy matter. So the gas that was there now just changed phase into a liquid, but the mass is still there. So then when we're done, and it's room temperature again, and you've only got the flask, the small aluminum foil, and the copper wire together, put it in your balance. Just make sure it's dry. Right? And that's the weight with the unknown. Right? So you subtract the before and after, you get the weight or the mass of the gas. Right? You're done. All you have to do now is calculate and compare the molar mass to the table and tell me in your report, because this is a formal report, tell me in your report which one is it. Okay? All right. Now again, I repeat myself because I think it's necessary. When you're writing your formal report, you don't regurgitate the procedure. The procedure here in the hard copy says do this, do this, do this, do this. That's what you put in your lab notebook. What you put in your report is this was done. So you write the report as if you were there and did it with those steps. All right? Use third person passive past tense. Okay. So now that we've got all the data, what are some safety issues, right? Because that's part of your formal report. You've got to identify the safety issues. I'll let you think while I'm erasing the board. All right, so what's possible? What could go wrong, right? Well, you got boiling water, right? You got hot water. You got a hot plate. Potential burn issues, right? You've got a volatile gas, and these gases are organic compounds. Most of them are not going to be hazardous. But if you sit there and sniff it as it comes out of the top of your flask, sniff it long enough, I don't know. They say you could kill some brain cells with it. If that's true, then I've killed a lot of brain cells over the years because there's just no avoiding smelling some of these things. But there's a potential hazard there for, particularly if you have a pre-existing condition, a lung condition. It wouldn't be good. And these are organic compounds, so what does that mean? That means they're flammable, right? So the liquid's flammable as you dispense it, and the gas is flammable as it escapes. So you don't want any open flames anywhere near these, right? Flammability. Okay? And then there's always the issue of glassware. Right? You could drop it. You drop a piece of glassware, right? And what does Murphy say about a dropped beaker? Will send pieces everywhere. You'll be picking them up months later in corners on the other side of the room. Okay, so what else? So if you protect your eyes, protect your hands, lab coat, closed-toed shoes, cover exposed parts of your leg. Right? That's if you were in the lab doing this hands-on. Those are safety issues that have to be in your report. Okay. Now, where are potential errors, right? Where could you go wrong? Well, let's see. You could have weighing errors. Right? If your beaker's hot when you put it in there, you're never going to get it to settle down. Right? You won't get an accurate weight until it's room temperature. We talked about one earlier. You could have moisture collected on the under the aluminum cover, right? That would be a problem. Temperature. You could read the thermometer wrong, right? I've talked about that. I don't know if I've talked about it. I'll just say it again. The most common problem with reading a thermometer or any glassware that's calibrated is called parallax error. That's where you have a piece of glassware, any glassware, and you're trying to read the level of something in here, but the mark here, and say your eye is up here instead of level, then you're going to think that you're reading that volume instead of eye level, which would read that volume. That's why glassware usually and periodically has a line that's scored all the way around. Because if you only see one line by looking at it, you know the level. If you see two lines, that means you're either too high or too low, and you're seeing the front line and the back line. Right? So you got to read it correctly. All right? So that's a possibility. You read the temperature wrong. I'll let you think about some others. Otherwise, this video will be way, way too long. All right, so let's do a sample calculation. Right? there's one in your method, you know, for practice, example. But I made this one up. Let's say the barometric pressure that we measure in the lab is 29.17 inches of mercury. Right? You know it has to be in atmospheres to use the formula and to use the universal gas constant, R, that we have chosen. Right? So we would divide that by 29.92. And that would give us atmospheres. How about volume? Well, we're going to measure it in milliliters, but it has to be in liters, right? So 150 milliliters is 0.150 liters. The flask with just the cap on it, the empty weight, is this. And the flask with the cap and the unknown in it is this, right? So what's the mass of the contents of the flask? Well, you have to subtract the smaller one from the bigger one. Right? So that means you have to know how to operate your calculator. So 96.9698, subtract the smaller one, 96.5579, tells me that the mass is 0.4119 grams. Okay? And the temperature. What are the units for the temperature? Always with gases, it's Kelvin. A lot of other places it's Kelvin as well. So you had 273. All right. So there you have all your values converted to the proper values. Now let's do the calculation. All right. So we need to use, we already know the mass, so the molecular weight is going to be the mass divided by the number of moles, and the mass was 4119. We just need the moles, right? So how do we get the moles? PV equals nRT. Solve for N, so these two come over here. All right. So what was the pressure? Oh, we didn't finish that calculation. So 29.17 inches of mercury divided by 29.92 is 0.9749 atmospheres. Volume is 0.150 liters. R is 0.08206 liter atmospheres per mole K. I don't have room to write it in there. And temperature is 373. Okay. All right. So you just solve that equation, and you find out how many moles. 0.9749, 0.15, 08206. 373, and I get 4.778 times 10 to the minus 3 moles. Okay? So we should take this value and divide it into that number. .4119. I get 86.2 grams per mole. All right. So what gas is that? Well, let's see. We need our we need our table to pick out which gas we have. Have to find it. Here it is. All right. So there's your table. Same one that's in the, this is the key, but same one's in your student version. So 86.2 is Not on here. Right? So what could it be? Well, let's see what they say it is. They say it's hexane. Oh, I was looking at the wrong column. Yeah, 86.2 is hexane. All right. So you've got a sample in there, and a sample problem to work. It's really very simple. You just break it down into steps, and you know where you're headed. You're headed for that. You need to know that and that. How do you get them? We know how to get that one by difference. We know how to get this one by the gas law. Right? Then you take those individual steps. Right? That's how you solve a complex problem. You break it down into manageable pieces. All right, so you've got pre-lab questions and post-lab questions that have to be answered. Let's see. Yeah, I'm not going to answer those for you. I will give you a hint on this one, just to show you that I'm human. Post-lab question number 1. Calculate the volume occupied by 1 mole of gas at 1 atmosphere at 0 degrees C. This is known as standard temperature and pressure for gases. Temperature is 0 degrees C, which is what? Okay. Pressure. Standard pressure is 1 atmosphere. And we're given moles, right? And what else? That's it. The question is, what's the volume, right? So how would you solve that problem? You got the right units. You've got an equation, right? We know that one, we know that one, we know this one, we know that one. Solve for that one, okay? Just almost gave you the answer. So that was post-lab number 1. Okay. Post-lab number 4 is another exercise in calculating the molar mass and then picking out the volatile liquid that belongs to that molar mass. Right, so you're still going to use that table. Right, those are post-lab questions. Pre-lab questions are in here somewhere. Here we go. Pre-lab questions. There's another sample problem. Okay, you can do those. All right. So let's see what else, if anything, is missing. The data. All right, so this video will be published shortly and posted in Blackboard. So you have those 3 things. You'll have the hard copy, you'll have the data sheet, and you'll have this video. Right, so you can go back and look at the video. If anything puzzles you, you're stumped. All right, good luck.